Here is the question that I ended the previous part of this video lecture with. So we have a situation here where the system had a bunch of kinetic energy because the clay was moving. And after it hits the wall, the clay isn't moving anymore. So this system definitely lost kinetic energy. And so kinetic energy in this system must have been converted into internal energy. And so the system must have gained internal energy.
To get a further idea of this picture, let's talk about what elastic means, because you might have been wondering about that. So we talk about elastic collisions, but in everyday speech we use elastic to mean things that are springy, things that tend to return to their original shape. Things where the changes in their shape are reversible. Well, that's familiar, isn't it? Reversible. So things like balls, rubber balls, springs, elastic bands, we would refer to these objects as elastic because the changes in their shapes are reversible. On the other hand, inelastic things are deformable. You often would call them plastic, which just means moldable, right? You can mold them into shape and they stay in that new shape. So changes to their shapes are irreversible. Things like clay, bread dough, wax. And so you can go to the swimming pool and you can go up on the diving board and take a jump. And so you have a bunch of kinetic energy, you land on the diving board and your kinetic energy is converted into internal energy in the diving board. And then, because it's quite springy, it returns all of that energy to you and you have a good amount of kinetic energy and do a good dive. On the other hand, you can go to a swimming pool with a really cheapskate owner who got a great deal on a wax diving board, and now that doesn't work because your kinetic energy gets converted irreversibly into internal energy in the diving board. Internal energy is just a broad category of types of energy. It's useful to start talking about the types of energy that we refer to as internal. They're all associated with state changes. Remember, the whole idea here is that we're associating changes of state in the system with the internal energy changing. So when a state of a system changes in a particular way, we say there's some particular type of internal energy that's changing. So for example, when some part of our system changes shape, but in a reversible way so that it can spring back, then we call that spring energy, or sometimes you'll hear it called elastic energy. When something changes in an irreversible way, there's also some sort of internal energy change, but we don't call that energy spring energy. We reserve the term spring energy for reversible changes in shape, like what springs do. If the temperature of the system changes, then we say the thermal energy of the system has changed. And if there's been a chemical reaction, then chemical energy inside the system has changed in some way. So we've seen that internal energy is extensive, and we saw in the last lecture that kinetic energy is too, so all of these energies are extensive. They'll follow the same accounting scheme as other extensive quantities. So one thing that's interesting is the situation where there's no transfer in and out, no input or output. So we need a name for that. Just like we called a system with no input or output of momentum an isolated system, we're going to call a system with no energy input or output a closed system. And let's look at a quick example. Let's think about our cart and spring. Well, first of all, the cart and spring is our system. Is it isolated? Well, no. It starts off with zero momentum. It ends up with a momentum to the right, and we know that momentum is conserved, so that momentum must have come in from outside. On the other hand, is it closed? It starts off with a bunch of internal energy in the spring, it's spring energy. That's all converted into kinetic energy, but the spring and the cart are both in the system. And so no energy left the system or came in, it is closed, even though it's not isolated.
Identifying a closed system can make analysis of a situation much easier, and in principle it's easy to do, but in practice it's often challenging. Look around at the process you're thinking about. What objects in its vicinity are changing state?
Draw your system boundary just to include the ones that are changing state. If you've got them all, then you should have just defined a closed system.
Let's look at a specific and reasonably simple case of this. Suppose we take a ball and we compress a spring and we use the spring to launch the ball into the air. So if we want to know whether our system, and note I haven't defined my system yet, but if we want to know whether our system is closed, we need to look for state changes outside the system. In other words, we want to know whether there were changes to the system that were accompanied by changes outside the system. Now, for most people, this is quite counterintuitive when they first see it, but I hope this example is going to make it clear to you, and in any case, practice will certainly make it clear to you. I'm going to define my system first as just the ball, and let's see what happens when I do that. So clearly the ball gained kinetic energy. We believe energy cannot be created or destroyed. And so if the ball gained kinetic energy, the question we ought to be asking ourselves is, where did that kinetic energy come from? It can't have just been created. It came from somewhere else. Well, there was a state change in the environment. That tells us that the environment's energy changed. And so a perfectly reasonable explanation for where the kinetic energy of the ball came from is that the environment lost energy. That energy was given to the system. And so, since energy moved from the environment to the system, this is not a closed system. So now let's try a different system definition and see where that gets us. So let's instead think of the ball and the spring as our system. And again, let's ask where the gain in the kinetic energy of the ball came from. Well, there were no state changes in the environment now. And so the environment's energy can't have changed. Well, if the environment didn't lose any energy, it can't have given any up to the system. Similarly, it didn't gain any energy, and so the system couldn't have given energy up to the environment. Well, that's already enough for us to say that this system is closed. There's been no energy into or out of the system, and that's what we mean by closed. We can think further then about why the ball gained kinetic energy, and now the way we would explain it is that there was a state change inside the system. The spring, which is in the system, changed its state. And so it's reasonable to suppose that what has happened here is that internal energy inside the system got converted into kinetic energy. I'm going to finish this video by just raising a really serious problem of terminology, and it's that people don't use this terminology consistently. I hope I've been clear. I mean no input or output of momentum. When I say isolated, I mean no input or output of energy when I say closed, and we're never going to allow matter to enter or leave a system, so we don't need any terminology on that. If you go on and do thermodynamics, you'll find that people use the terminology differently. Input or output of momentum just isn't really an issue in thermodynamics, and so it just doesn't get mentioned, but they use isolated to mean no input or output of energy, and closed to mean no input or output of mass. And in advanced dynamics, they tend to use the terminology we do, though they're usually not clear about saying that they're never allowing matter to enter or leave a system. The worst case is intro physics textbooks, where they often use isolated both for no input or output of momentum and for no input or output of energy. That is idiotic to use the same term for two totally different ideas. Anyway, I hope I've been clear. As you go on, you should be aware that people do not use this terminology consistently. So check, find out what they mean by isolated and closed.